Hello everyone, and thank you for coming at my talk. Today we are going to talk about my experience and the experience of the project I'm running about HTTP benchmarking. So first of all, thanks Devoxx for having me today. I'm really glad to be here in Poland. And let's begin. So this is a blog post that was posted in 2013 by a company called TechEmpower. And basically, this blog post, it was doing a performance comparison of 20 frameworks, 20 web frameworks, written in different languages, and like PHP, Java, etc., of course. And basically, the idea is that when you will write an application, you care about the performance of your application, of course, but you care also about the performance of the web stack that your application will run on. We all heard the stories about applications being written in a different language because the performance expectations were not there. And we all know, of course, that for user experience, performance matters, and most users will expect a website to be responsive in less than 2 seconds, and usually after 3 seconds, users will just start to give up and go on another page. So let's quickly review the expectations that this benchmark sets. So first of all, what is really interesting about this benchmark is that there's a community around it. It's not a closed source benchmark, it's open source. So you can find it on GitHub. And on GitHub, basically, there is a big repository where all the frameworks are integrated. And if you want, you can take it and run it on your own hardware in your own environment. Or you can try to improve existing benchmarks or add benchmarks for new web stacks that are around there. And I think it's important to say also that it's not, you don't have to be maintainer or owner of a web framework to contribute to it. Anyone can contribute. It's not reserved to the maintainers. In our case, for Vertex, we mostly take care of it, and that's the case for a lot of frameworks, but there are some frameworks which are not maintained by the original authors. So today, it's more than 400 frameworks in 26 languages. There are 5 tests. We will not review all the tests, but basically, what is interesting here is that there are 2 kinds of tests. The first kind is, it only tests HTTP server. So basically, there is no backend. So we really test the performance of the server. And the other kind of test use a more classic design with a database. So there is a database involved, and there is asynchrony and networking, more networking involved in this setup. There are some strict requirements, so there is a list of requirements about what you can do and what you can't. Like, for instance, if you access a database, you can't cache the rows coming from the database because we want to test the performance of the web frameworks that will access the database. And it's run on physical server or cloud. And also, what is really interesting is that now there is continuous benchmarking, which means that the benchmark runs continuously and you can see the results. And that's really interesting because when you do modifications, the only way you had before is to run the benchmarks on your hardware, which is what you should do, of course. But they have their own hardware, their own setup, and maybe it could behave differently on their setup. So when you submit something, when you submit a change, you can use continuous benchmarking to see if you have improvements or regressions, things like that. So we are going to talk about the performance of Vertex. So this talk is not about Vertex. If you want to learn more about Vertex, you can look at the documentation. But basically, I will try to do like a lightning introduction to Vertex. So Vertex, it's a toolkit for building reactive applications in Java. And in practice, it means that you write non-blocking applications. And instead of having your application being, like one thread that will execute everything, your application just, every time there is asynchrony involved, that means it's not CPU code running anymore, like doing, for instance, database access, then we will just not get the result right now, and we'll set like a continuation to get the result later. And as a result of this, most of the time, the CPU, one core, will execute all the tasks of the applications. And this execution is done on an event loop. And it's really what we could call event-driven programming. So if you are familiar, if you have written GUIs like Swing, or if you have written front-end like Node.js, or even plain browser code, you are certainly familiar with that. Vertex provides a stack for building applications. So we not only provide HTTP, although today we will focus on this. We provide a set of components for many kinds of database access, for Kafka, etc., etc. And that's it. So the project has been created in 2011. It's pretty popular. It's it's almost 10K stars on GitHub. So I'm lying a bit. And so if you want to give a star, so we can reach 10K faster, we are like 9,700 and something. And it's written on top of Netty, which is a great framework for writing networking applications. Shameless plug, we also have this book being written. So I will not tell you to buy this book, but if you want to go further, you can also buy this book, and it's in EAP today. And I think it's going to be a great book. So let's begin with the story. So in 2013, the blog post was kind of considered as the first round of this benchmark. And you can see that periodically TechEmpowerer makes new rounds. And each round is basically, they do like 2 or 3 rounds a year, it depends. But in 2013, at round 8, Vertex was already popular. And part of what made Vertex popular is TechEmpowerer, and that Vertex performed better than the other frameworks. But 3 years later, at round 14, we can see that Vertex is performance are not great anymore. And that's what we are going to look at today. So what is important here is not to look at the rank of how much Vertex is, but more at what's the ratio between the fastest and Vertex. And of course, in 2013, at round 8, it was the fastest. It was 100%. And in 2017, it's like 27%. So, and that was the performance for only HTTP server. When we look at Vertex running with a database, then performance were not great either. Like here we can see that Vertex is like 42 and 20%. And in some cases, like with Mongo, performance was abysmal. Like PHP was faster than Vertex and Java. So, and the problem it raised is that people on the list, on our Google group, started to complain, and they asked questions like, Vertex seems to be sliding downward the list, or starts are not really good for Vertex. Is Vertex not good with database, or are the benchmark plain wrong? And today I will talk to you about this and what we did to improve this. And so, quick introduction about me. I'm Julien Viet. I've had the opportunity to start to develop open source software since 2003. And I started to contribute at JBoss application server back at this time. And I was fortunate enough that I was hired to do my passion. And basically, they came and they told me, okay, we are going to pay you to do what you are currently doing for free. I say, okay, no problem. I'm signing. I'm all in. And today, I'm the Vertex project lead. I'm coming from Marseille. I'm French. You can tell by my accent. You can follow me on these social medias. And I'm also Marseille Java user group leader. So if you have an interesting talk, something to say, and you are nearby Marseille, you can reach me directly, and we can arrange maybe something so you can talk at the Marseille Java user group. So first, let's define a few expectations, which are really important concerning benchmarking and what we are going to see. So first, benchmarking is not a simulation. It's not, maybe most of you are used to simulations, like you are going to set virtual users with a scenario and with a shopping cart and everything. And benchmarking is not at all about that. It's a bit similar, but it's really about trying to go as fast as possible. And there is no question of business, or sometimes it's not a related use case. It's just something just to measure. If you're going to be in a benchmark, then you want to measure and don't guess. So it means that basically you have to set up this virtuous circle where you run performance, you define, you measure, you try to improve, and you run the benchmark again, and that's, well, I'm a bit captain obvious on this, but that's how most people do. And of course, to do that, you have to measure, and when you measure, you have to be sure that you are measuring the correct thing, so it's not always easy, and I will not talk about that later today, but there are great talks about that exists. Define a baseline. So basically, when you want to do that, you have to compare. So either you want to improve, or you say that's my expectations, and I want to, and that's my baseline. And you also have to define expectations. So what is my goal in this benchmark? Because it might never, I mean, you might never reach this goal, or you might, but if you don't set a goal, you basically, you can continue to do the same forever, of course. Today, so it's not a talk about these tools, but that's the tools I used, and we are going to see how, I mean, what kind of results we can get from those tools. So basically what we do is that for those tools, we run everything on the JVM. The JVM is very fast, but it's very hard to understand, when there's a performance problem, it's very hard to understand, to know what is the actual cause of the problem. And there can be many causes, like it can be locking, it can be CPU, not CPU used correctly, it can be networking. So in our case, the tools we are going to use for most CPU profiling are async profilers and async trace. And then we'll use flame graphs. So flame graphs is not a benchmarking tool, it's a visualization tool. So basically, when you have a lot of complex data from benchmarking, you want to understand quickly and easily, with intuition, what is going on, and that's what flame graphs gives you. And there's also, when you do that, another way to get interesting data are JVM logs. And there's a tool called JIT, and that's also very interesting because I will explain later that the JIT performs a lot of optimizations, and JIT helps you to make sense of what happened in the JVM when you were running your performance benchmarks. So let's start first with the plaintext benchmark. So that's the name of the benchmark. So that's a simple hello world. So it's a static response, mostly static response, because there is a date HTTP header, so it's not always the same response, but basically the body of the response is the same. It uses HTTP pipelining. That's something we are going to explain later what it is. And it does a best of there's a typo, best of 256 up to 16K connections. So basically you have at most 16K connections. And the benchmark will use the best result from the perspective of the client. So the first lesson we learn is that we have to badge rights appropriately. And so basically, this is important. This is about concurrency. So concurrency is how many things can I do at the same time. And if you look at the HTTP protocol, HTTP 1.1, because this is what is used in TechEmpower Framework Benchmark, basically the client sends a request and using one connection, so it borrows one connection from the pool, and it cannot use this connection anymore until it gets the response back. So it means that if the website takes a lot of time to respond, I will just choose this connection for normal requests, and then I have to borrow another connection. And of course, when you have used all the connections, you cannot do it anymore, so you cannot run more requests at the same time. And pipelining is a kind of hack to improve performance, to improve concurrency. Basically, the idea is that instead of waiting for the response to come, I have this request, I know I want to send it, I will send it anyway. Will the HTTP server process it faster? No, because most of the time the HTTP server will simply process the connections, and then when it has finished to process the connections, it will send back the result and read the new connections. And what it will improve is that you will save the networking time, the round-trip time between the client and the server. So instead of, let's say, if there is 1 millisecond between your client and the server, instead of waiting 2 milliseconds, if the HTTP server response time is instantaneous, you will just send the connections and you will get the result after. So it's really a way to improve concurrency. So let's have a look at flame graphs. So this is not about I mean, this isn't a talk about flame graphs. You can also read a lot about on internet, but I will try, though, to explain you briefly what it is. So let me find the correct flame graph. So flame graphs are generated as SVG files. So basically, that's the one you want to see. And this is a typical flame graph. Let's click on this. So basically, explanations. I think the most important thing to say about flame graph is that most of the time people expect that the x-axis is the time, and it's not at all the time. Basically, the x-axis means basically the importance of the performance. So the largest it is, the most important it is and affects the performance. And vertically, the y-axis, it's about Java stack traces. So basically, this is a kind of representation of our program running. So it's like a picture of it. And it helps us to make sense of what takes time and what doesn't take time for the CPU. So we can see that at the very bottom, you have a Java lang thread run, and that's our thread running. And of course, we are in this run method, and it takes all the time, so it takes all the x-axis. So we are not going to review everything now, but what is important here is that if we look at what is going on when we write, when we do I/O with the JVM, at some point there is, you see this red bar. Basically, this red bar is a call to the system, that's a system call to the write on Linux. And so we can see that in this case, for this benchmark, so that's non-pipelined HTTP access. We can see that it takes like 23% of the time is spent doing this system call. And if we don't take special measures, like basically if you will flush every time to the network, every time you have an HTTP response, that's what will happen. And if you have pipelining, with pipelining, basically, you receive several requests, HTTP requests at the same time. So when you receive the request, you have like this packet because the requests are very small. And likely the server will process them as a buffer, and the buffer will contain all the requests. And what we do in this case is that we flush all the time. And if we do that, we can see that now it's 46%. Why? Because we receive 16 requests, pipeline requests at the same time, and for each request, we do a write on the socket, and this write is much more expensive. And so what we do in Vertex, and I think it's not only in Vertex, there are also frameworks that do it, is that instead of flushing everything, after every HTTP request, we flush, actually, we just received 16 requests, so we know that we will not have network anymore, read involved anymore for this. So instead of flushing at every request, we will flush every 16 requests. And that provides, of course, a performance improvement. And now we can see that the write here, it only takes 16% when it processes 16 requests. So that's quite important. So you need to learn how to batch appropriately and make sense. Sometimes CPU, bottleneck is CPU, sometimes it's network, and in this case, just with this simple trick, we are able to improve a lot performances. Second lesson, it keeps your method small to ease compilation and lining. So when we did some improvement in Vertex, we added this piece of code in a Git commit. And in our performance benchmark, we measured like a 3 to 5 performance penalty. And we wondered, why does it happen, right? Actually, if you look at this code, it treats, that's an exception handling, like it's a special case of HTTP. So when you run this code in a benchmark, actually, this piece of code that we added, it's never called. It's not even, it's not called by, so why does it affect so much performance? So much, 3 to 5% is a lot when it's already optimized. And what is important here to know is that, to know a bit about the JVM and the JIT. So basically the JIT is what takes Java bytecode executed in the JVM and transform it into native language. And what does the JVM is that it optimizes for the hard pass, and there are a lot of optimizations it does. It's very smart, and basically that's what makes Java and the JVM very, very fast. Basically, if you have a server and you use it in some way, it will profile it, get statistics, see what is often called, and just generate the best code it can for this execution. And one of the optimizations is called method inlining. And method inlining, basically, it's very simple. I take a method, this method is called, I just take it and I put it in the caller. So of course, I save a method call to do that, but also what is important is that method inlining allows to open the door for new optimizations. So that's why method inlining is very important. So this code, actually, it's where we added the code. You see the new exception, the new code, I think it's this one or this one. No, it's here. But basically, I don't want you to read this code or make sense of it. What is important is to see it in globality. And if you want to make sense of this, you have to use another tool that is called JIT. So JIT, it's a very nice tool as well. So no, it's exactly, no, I failed. So here it's configured as a Maven plugin, and when you run it as a process, you can have a GUI. And basically, when we run the benchmark, we use specific JVM switches, and the switches will output a lot of text in the log. And basically, then you take this log and you give it to JIT. And now I start and I open it. And it gives you a view of all your Java packages, so you can have an understanding of what happened at the JIT level. So in this case, let's just go straight to the point. So the method name is process message, and basically, let me try to do this bigger. So it's written, I think, in not in Swing, but in the thing that replaced Swing a few years ago. And basically, what we want to see here is this class. Well, that's an inner class. And here we have two methods. So sorry if it's a bit small. Here you can see all the methods. And for all the methods, what is nice is that you can see, if you click on it, you can see, of course, the Java code. So that's the code of do message received. And you can see the bytecode, of course, here in the middle. And what is interesting, if you know assembly and CPU and you know all of these things, is that if you configure JIT and the JVM, if you configure the JVM correctly and you give it a plugin that is called HSDES, you can see the assembly code that was created by the JVM. So, I mean, it's really reserved to experts. I will not pretend I can read it. I can kind of make sense of it. I used to do assembly code, you know, but on Amiga 68K processors, which are much simpler, and I never learned this kind of CPU, so I really don't know. But anyway, what is interesting here is that we have the chain, and that is what is really important and what we want to concentrate on. Basically, you have this method do message received, and this graph is very interesting because it tells you what is inlined, what is not, and the reason why it failed to inline. And that's what we want to understand about. So everything that is green, it's great. You see? It means it's inlined. And everything that is red, it means it's compiled, so it's assembly code, so it's nice, but it's not inline. And the reason is why isn't not inline. And the reason is that if you look at process message and you go on it, so it's quite small. I'm sorry for that, but basically it says inline no. Why? The reason is that the method is too big. So if we go back here, actually, why I choose this picture is that you can see that the method is big, and adding this small chunk of code that is exceptionally called just made the method a bit bigger. But being a bit bigger, it crossed a threshold, and then the method could not be inline anymore. So the solution was quite easy. Here, that's the error processing. That's the code that will actually be invoked, and that's processing a body. And since in our case, we are simply processing an HTTP GET, there is no body, we don't handle errors. So this is quite simple, we just do a refactoring. We take all this piece of code, we pull it in a handle error. And this one is handle content. And so we reduce, and thanks to that, we are able to reduce the size of these methods. And so it can be inlined again. And by design, we choose to not put that in a method because it's what is always executed. And the reason why we do that, we could do that. And if we do that, likely the JVM will take this code and inline it because it's very frequently called in this benchmark. But there is, as I told you, there are limitations for inlining, and one of them is the size of the method. The other is, of course, you cannot inline too deep. So if we had a new method, we had another stack, and it will basically not be useful for this case. Last one, and that's the last one for CPU optimizations. Basically, avoid unnecessary allocations to reduce GC pressure. So we are going to reason, so that's, I think, the other piece of code I have in my talk, and then after it's done. But basically, we are going to reason about this part, and it's very easy. That's code that is really easy, and so basically, we focus on this, and this will be executed, so it's quite easy to understand. And here, what is important is that we use a lambda, and we call this, that's a runnable, and we just call it. And when we run benchmark, what we found is that, so with async profiler, you can, what you have seen so far is CPU benchmarking, but what you can also measure, not benchmark, with async profiler, it's the allocations. So here I do have another one that is called alloc. So that's a flame graph, and basically this flame graph is not about CPU, it's about allocations, object allocations. And of course, the JVM is very smart. There's GC, usually you tune GC to get the best result. But in these scenarios, if we can save allocations, it means we just save, we just don't create a future workload for the GC. And what we want to see here is, so you can see everything so it's not all JVM allocations, but it's the most important ones. So when we do have a request, here in the channel read methods, you can see, for instance, that there are some allocations done binary to allocate HTTP headers, to allocate strings. And is that something we want to look at? No, we don't, because when you process an HTTP request, you expect to have a string with the headers. So we are not going to not create the headers, because otherwise you could not run your application, basically. But we can review everything, and what is interesting here is this one. If you look at it, yes, let's make it bigger. I think we can make it bigger this way. I should have done that before. And basically, it's because we have a lambda. Usually the lambda, they don't require to instantiate objects. But in this case, we are using a lambda that is a capturing lambda. What does it mean? It's quite simple. Here, this lambda is keeping a reference on the message. And so to keep a reference on this message, it means that this lambda is not stateless. It means that every time I need this lambda, because I need to create a new instance. If I will not refer on that, then the lambda could be cached, and the same instance of the lambda could be used as a runnable. So what we did is that simply we added a new methods where we just pass an object and we give it a consumer, and when you run it, then you get back the object you passed, and so you don't have to make a reference anymore. So we just did these simple modifications, and thanks to that, we were able to eliminate this bottleneck. So let's make a quick conclusion. So what the kind of bit? So of course we did many optimizations. That's not all the optimizations we did, but that's what I selected those three because I think they are the best to talk about. So one is minimize flushing, of course. Optimize for the JIT. Sometimes you can have really weird things, and that's always interesting. And the last one is keep GC cool if you can. That's important. And thanks to that, at round 15, we got much better performance. Like now you see Vertex, it's 11. So here what is important is not to see that it's 11, because at this moment in the benchmark, so many web frameworks were added that it changed a lot of things. Because if you look at all these frameworks, libraries, I need to mention it, sometimes some of these libraries, they sacrifice usability in terms of the code you write for performance. And in Vertex, we try to get the best performance, but we don't sacrifice usability, so it's always a trade-off. So in this case, what is important is that we can see that at this moment, we were like 90% of the fastest. And as I said before, what is important is to define a baseline. And in this case, actually, as I told you, Vertex is based on Netty. And the question is, can Vertex be faster than Netty? And the answer, yes, it might. Maybe if we make a better usage of bare Netty, because Netty is a library, it's not a framework. So if you use Netty incorrectly, you might get wrong results. But what I want to say is that today we are not trying to be for this benchmark plaintext, we are not trying to be the fastest. We are trying to get the same performance than Netty, because we know it's very hard to. Sometimes it's a bit better. Well, that's called variance, and that's not very much important. So now let's talk about database benchmarks. So what is interesting is that we have 4 benchmarks, which are called DB, queries, fortunes, and updates. So DB is just a simple, the application, we just do a simple query to the database. Queries, it's the same, but it will execute this query like 5, 10, 15, or 20 times. Fortunes, and updates, we are not going to talk about that today. It's about doing updates to the database and all these things. For the benchmark, you can choose between 3 different databases: MySQL, Postgre, and Mongo. And it seems to me that the best results today are achieved with Postgre. And it's also important to notice that it's only 256 connections, and that has a lot of importance. So at 114, what we found in our investigation is that the best performance were actually defined by JDBC plus Ikari connection pool. That's what is giving the best performance in Java. And Vertex was using JDBC with a worker pool. So basically, we use a worker pool to be able to block. And actually, in this benchmark, blocking is not really an issue. And you often hear that non-blocking reactive can give great performance and better scalability, and that's true when your application processes a lot of concurrent requests. When you want a lot of concurrency, like I want my application to manage 10,000 requests per second and this kind. In this case, it's only 256 connections, and if you run it on a 32-core CPU, it means that each connection will have, each CPU core will only handle let's do the math, like 4 or 8 concurrent requests at the same time. So it's very fine to block, and CPUs, blocking model will never be a bottleneck in this case, and actually it will even be faster because there are a lot less synchronizations, and it might run faster. So tackling the problem, yes. What we did is that first we chose to focus on Postgre, because that was giving the best results, of course. And previously I said that we had really bad results, like, abysmal MongoDB results, and those were actually mistakes because we didn't spend time on those benchmarks. So for Mongo, it was a missing index, and for updates, we didn't use a transaction for doing the update, so it was much slower. And so what we did now is that, as we wanted to understand, we wanted to have like a non-blocking Postgre client to see if it makes a difference. So we started to write something called the reactive PostgreSQL client. And so it's a fully non-blocking on top of Vertex client for JDBC, not for JDBC, for Postgre. And the goal is to be simple, clean, non-blocking, performance, and lightweight. And the non-goal is to be a driver, so It's not low level, it's a bit higher level, but it doesn't aim to be things like, data, object mapping and those kind of things. You just give it SQL, you execute it, you get the results, and we do the best it does the best to give the best performance, of course. Non-goals, yes, it's not an abstraction. So the project already exists on GitHub, and now it will be part in Vertex 3. So it was created in an incubation, kind of incubation, and in Vertex 3.8, it will be part of the stack in Vertex 3.8. And in addition, it will provide also support now for MySQL and soon SQL Server. So I said that before the goal is not to be an abstraction, but now it starts to be an abstraction. So let's see the irony. So what is interesting here and important is that if you have interest in protocols, and that's a great thing, basically the performance model is when you have distributed things, like simply your database accessed by your server, the performance model is often defined by the protocol. So we have seen that before, that with HTTP, you have one request and one response at the same time. And of course, the performance of this is defined by this model and also by the round trip between the database and the server, and also by the query execution time. And if you want to do more requests at the same time, we have seen that one way is to do HTTP pipelining. Now with HTTP, you have HTTP2, and HTTP2 is great because it allows you to do multiplexing, so basically use one connection to do many requests at the same time. It means that on the client, you don't need anymore to care about the size of the connection pool as a side effect. And basically, the idea is that when you use Postgre, or I think most database, I'm not familiar with the protocol of most database, but I spend a lot of time on Postgre. And basically, it's the same as HTTP. You have a command, and you send a command to Postgre, and then you get a response. And all the operations you do with your clients are going to be translated into a set of requests and response. So the idea was, why don't we try to, we want to be faster. What is the bottleneck? The bottleneck is of the protocol in this case. And so the idea we had is that why don't we try to pipeline to Postgre? So when we execute a request, we send a command. But when we have another request that is coming, another query we want to do, we execute a command. And so we send already this command. So we save again the round trip time, part of the round trip time between the client and the server. And so does it help? And the answer is yes. It helps. It improves concurrency and performance. So that's a small benchmark I wrote. So basically here we just execute 5,000 queries and we pipeline them, and we do that assuming that the latency between the client and between the database and the server, which is the client in this case, is 100 microseconds. And we can see that on the x-axis is the pipelining level. Basically, it's how many requests we can send at the same time to the server. And we can see that with JDBC, of course, as it's blocking, we can always do one, so this number doesn't matter, and the performance stays the same. And we can see that the effect of pipelining, if we take 4 pipelining, then we have much better performance. You see? Then it starts to amortize. I think it's important here to say that this kind of optimization, it doesn't work for everything. It just works for special case. It works when basically the time between the round-trip time between the server and the database is much lower than the query execution time. Of course, if you have queries that takes a lot of time to execute, then this will dominate the performance, and pipelining will have no effect. But in the case of this benchmark, we are just using simple queries, which are in cache, and that's very fast for the database. Basically, I don't know how long it takes to actually do the processing of the request, but it's very fast. Now, what is interesting is to see the impact of the latency on this performance model. And basically, that's the same test, but here, instead of being 100 microseconds, it's 1 millisecond. So 100 microseconds between your client and your database is already very good. It's a good result. 1 millisecond is maybe more what you have in the cloud and this kind of environments. It really depends. And here we can see that pipelining has a much more interesting effect. Like if you pipeline 16, you can see that the performance are much, you can see more than a noticeable improvement. Actually, I haven't looked at the factor. So where does that put us? Basically, the idea is that we checked in that, and then we just send, okay, let's see the result. And thanks to that, at 115, Vertex was, with Postgre, was the best result. So we basically went like from 20% to being at the top of the benchmark, which is really good. And if you look at, so that's the CI Java unofficial, so not the recent one, but it's like from last year. You can see that, so it's only Java results. You can see that there are a lot of Postgre related, and it's only Postgre. So you can see that the best is Green Lightning, then is Vertex Postgre, then Wizard HTTP, Ratpack PG client, Vertex, Micronaut, Spring Webflux PG client. So here I need to say that Spring Webflux is not done by the Spring, by Pivotal. It's done by external contributors. I think it's important to say that. But what is important here to say is that if you look at the POM XML of all these frameworks, they were all using the Vertex, the reactive Postgre client. Basically, even if you are not using Vertex, you can benefit from those performances when you embed Vertex and the PG client in your application. I think even this one without HTTP, basically what they did is they did a fork of the project. Unfortunately, we added many new features and the fork never cooked up. So, last words about this. So, as I told you, there is a community behind TechEmpowerer. There is a mailing list where you can discuss. And our results were so good that people start to, you know, when you are at the top, everyone looks at why did it go from one not great position to being number one? What's the reason? I want to understand. So people started to look at it, of course. And as I told you, there are requirements when you do benchmarking for TechEmpowerer, like you cannot use batching for doing HTTP, for doing database queries. So people started to wonder, like, you know, doesn't that conflict with the requirement that every query results in a forward trade to the server? So basically, is what we have done still correct according to the guidelines? Or, to be honest, I didn't really think about that because when we did it. Another one said, like, it seems like a violation of the round trip requirement, but the guy was positive. He said, it's a cool feature. He didn't say it sucks or whatever. Sorry for using this word. But basically, he said it's a cool feature. So I was like, okay, cool. That's me replying like, can you elaborate why it violates the requirements number 6? Each query sent, then I just say that we just respect the Postgre protocol and we just send the query before it's needed actually. And what we did is not, I mean, it's not rocket science, it's very simple, and that's actually, if you use Redis client does exactly the same thing. So that's a reply from TechEmpowerer. They said, in summary, we are leaning toward prohibiting pipelining. If there are more opinions, we'd like to hear them. So what is very positive is that they stayed open. Like, so they didn't close the door to this optimization. And finally, they conclude that they said, basically, they authorized it. They said, we believe it should be allowed. So it was great news for me because I was like, okay, all this work, all this great work that we did will not be useful anymore. That's, so finally, they said, we, TechEmpowerer, have decided to allow pipelining, and then they changed the requirements, and they said, however, it's permissible to pipeline traffic between the application and the database. So that's really cool, right? So I just have 1 minute to do the conclusion. I will do as best as possible. If you have questions, so 2 things. Before, if you have questions, we can talk to me. I'll be there until the end of the conference. I'm leaving Thursday. If you like this talk, give me a good rate or something. If you don't like it, it's fine. But I'm not professional speaker, but I would like to hear about what I can improve in this presentation. That would be very important for me. So finally, what did we learn? TFB, the TechEmpower Framework Benchmark, it doesn't favor non-blocking design. So in practice, it means like things like Vertex, Nelly, etc. They are not in the best position to get the best performances. With database, it's only 200 or 500 connections, request simultaneous connections. And with plaintext, it goes up to 16K connections, but there's no backend involved. So, well, doesn't make a lot of sense to me. JVM is a great place for performance. Today we have really this is really performant. You have really great tools. If you want to learn more about the tools and even about the blogs, like today you have many people, great people talking about blogs, or you can look at other conferences about performance. And I learned a lot by this, and I learned a lot by asking questions. Trade-offs, yes, trade-off between usability and performance. So when you do a web framework or kind of, you can get the best performance, then sometimes you have to sacrifice usability. In our case, we try to get the best compromise. In case of this, what was the actual bottleneck is the RDBMS protocol design. And by that, what I mean is that today we have HTTP1, we have HTTP2. HTTP2 is really a performance enabler. And it seems to me that database protocols were designed back in the 90s. So they were designed when performance did not matter that much, and they didn't have a lot of concurrency to handle. And what would be great is that if database vendors could just say, okay, we need better protocols, so we are going to write a multiplex protocols for the database. So on the client, we don't need anymore to have a connection pool, and just 1 or 2 connections will be enough to handle the concurrency, and the concurrency will be defined by the database and not by the connection pool, which acts as an intermediary. And last one, that's just what I said, protocol concurrency matters. Yes, if you have a protocol that just does one thing at a time, you cannot expect much from it performance-wise, and you have to open many connections. And you have a smart protocol that is well-designed, it's great, and it will help a lot for performance. That's it. The presentation is done. Those are the links you can read, and I can take any question now if you have time. The slides will be on speaker deck, I think. It's already are. Any question? No question, thank you.